In the last section of Chapter 1, we're going to look at something called least squares regression, or the method of least squares. So the concept is we have two variables. So in this case, year would be 1910, 1920, 1930, and so on. And the death rate per 100,000 people in the United States, 84.4 per 100,000 people. In 1910, 71.2 per 100,000 people in 1920, and so on. And what we want to do is fit a line that best represents the pattern in this data set. So if we look at the plotted graph, what we find is that the points are not exactly on a straight line. But what we want to do is describe with a straight line as well as we can what this pattern is, because the points do tend to scatter above and below sort of a straight line that cuts through the center of the pattern of the data points. So what we would do is, as in figure 16 here, go through and fit a line and then measure distances, vertical distances from the point to the line in each case. So we've got D1, which is almost on the line, D2 is a little below the line, D3 is a little above, and so on. And then what we want to do is in some way make the distances as small as possible. And what we're actually going to do is a method called the least squares. Now, in this case, what we're looking at is not just looking at the individual distances, the D1, D2 values, which is just the difference in the y-coordinates between the actual data point and the line, but we're also squaring those. That way you don't have positive and negatives canceling each other out. So in this case, if we take value of the point minus value of the line, and remember it's the y-coordinate, so it'd be what value is sitting on the y-axis in each case. If the point is below the line versus above the line, we would get positives and negatives. And we don't want those to cancel each other out. So what we do is we square each distance. And then we add all of those up. So the first distance squared plus the second distance squared, and so on until we have all of the n data points. We add those up, and we want to make that as small as possible. Now, a shorthand way to write a sum is using the capital letter sigma. So anytime you see this sigma notation, it means add up all the things following. So for example, x1 plus x2 all the way up to xn, just a sum of n different values, we could write in shorthand notation as sigma x, and it just means add all the x values together. The first point plus the second point plus the third point all the way up to the last, or the nth point. Now if we have sigma xy, what that is going to mean is take the product of x and y for each value, 1, 2, all the way up to n. So take each of the products and then add all those together. So that would be x1 times y1 plus x2 times y2, and so on. Now keep in mind that the summation of x squared means take each x value and square it and then add it together. So x1 squared plus x2 squared plus x3 squared plus all the way up to x sub n squared. If we wanted to just take the sum of the x's like we had up here and then raise that sum, the final result, to the second power, we're going to have to put that in parentheses to distinguish it from the sum x squared versus parentheses sum of x, close parenthesis, squared notation. So for the least squareds line, we can actually write this as the sum of d squared. Now to calculate the distances, we have the data points, x1, y1, x2, y2, and so on. Those are the actual points, and then the least squares line, if we plug x1 in to this equation, we would get a y value out related to that x1. So that we can distinguish between the actual data points, which are going to have lowercase y's, and what the line's data point would be. Those will be capital Y's. And then what we're going to do is take each distance and take the distance between what the line says the point should be in terms of the Y value of the data point minus what the actual Y value of the data point is. And we're going to actually square all of these things. So this actually turns out to be mx1 plus b. That's what capital Y would be, because that's what the line says the Y value would be at point x1, minus what the actual data point, y1, lowercase y1, turns out to be. And we would do that for all of the values. Now what we want to do is make this sum of the squared differences as small as possible. And we actually can do that in calculus, except it involves quite advanced methods. Technically in a math program, you're looking at what's called multivariable calculus, because the sum actually depends on two things: the value used for the slope of the line and the value you use for the y-intercept. So you actually have to do things that are much more complicated. So we're just going to talk about the formulas. Now the least squares line, okay, that gives the best fit to any set of data points has slope m and y-intercept b given by these formulas. And notice there's a lot of complicated looking notation in these formulas. But let's go down and look at what these actually mean in terms of our exercise. Notice that b involves the value of m, so we actually have to solve for m first in order to use this formula. So back to the example we had, what we're going to do is actually take, instead of the year, we're going to say years since 1900. So we subtract 1900 from each of the years. So the x values run from 10 to 100, and those correspond to the actual years of 1910 to 2000. The y values were the death rates. And what we're going to do is simply add the x values together, and we get 550. Add all those death rates together, and we get 595.5. So that's the sum of the x's and sum of y's. Now we also need some other terms. If you go back up, you need the sum of the xy products, as well as the sum of the x squared terms, and the sum of the x value squared, and I guess that's it. Okay, so now what we want to do is come down to our equations here and make sure that we have all of the values. So the next thing we need is sort of this green layout, the product of the xy's. So 10 times 84.4 is 844. 20 times 71.2 is 1,424, and so on. So this third column is actually the product of these first two columns. And then we want to add all these up to get the sum of the xy products, which is 28,135. So we have the sum of the x's, we have the sum of the y's, and we have the sum of the xy products. The other thing we need is the sum of the x squared terms. So what we need is 10 times 10, which is 100, 20 times 20, which is 400, 30 times 30, which is 900, and so on. So we need the squares of all of the x values here, and that's what's in this fourth column. And notice it's in this sort of orange or brown color. And if we add all those up, take the sum, it's 38,500. We also can do the same thing for the y squared values, even though we don't use those right now. So we really just need the first four columns. So the sum of the xy's is coded green. Now, how many data points were there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there were 10 values. So n is 10. There were 10 data points. The sum of the xy's, that's your green number, 28,135, minus the product of the two individual sums. So the sum of the x's is 550. That's blue. The sum of the y's was this pink, 595.5. In the denominator, again, the sum of the x's is blue, so that's 550, and we've got that squared term. And then we've got n, which was 10, remember. There were 10 different years. And then times the sum of the x squared terms. And that was that brown or orange color, 38,500. So then you multiply everything out, square things, do all your subtraction, and you end up getting a value of negative 0.5596 and so on. So we'll round that off to about 3 digits and just say that the slope is about negative 0.560. Now the next thing we want to do is use our other formula. So if we go back, B says take the sum of the y's minus m, which we just calculated, times the sum of the x's and divide by n. So we can go over to the next page, and what you can see is that the sum of the y's was that 595.5 minus what we just calculated m to be. And we really don't want to round this off yet. Okay, so we're going to keep what we had to 6 digits after the decimal point. And then the sum of the x's was 550. The sample size n, there were 10 data points. So when we do that arithmetic, we get 90.3 and repeating, so about 90.3. So then we can substitute m and b into the least squares line and say that the line that does the best job of fitting the data looks like a function where y equals negative 0.560 times x plus 90.3. Remember, x is years since 1900. Notice they give you a caution about premature rounding. So even though we are going to use the slope as just to 3 digits, when we do the calculation for the y-intercept, we went back to a lot more digits. Now it talks about how you can use calculators and stuff to do some calculations, but we're just going to sort of stop at that point as far as getting the equation of the line of best fit. Okay, if you really want to see how to do it on the calculator, you're welcome to go through that example, but we're going to sort of stop at that point. Now if we go on a little bit further over, we can talk about a couple of ways to use that equation. So what would you predict the accidental death rate to be in 2012? Okay, so in this case, 2012 minus 1900 would give me an x value of 112. So we're going to plug that 112 in for x to this least squares equation, or the equation of the line that we just found, and we get about 27.6. So we would predict that the accidental death rate in 2012 would be about 27.6 per 100,000 people in the U.S. population. Now we could go back and try to verify if we could find out what the actual death rate was during that 2012 year. Okay, so they make an observation that the death rate really began to go up after 2000 and was actually back up to 40.6 per 100,000 in 2006. So what might happen is that this linear pattern may not exist. It may not continue past 2000. There may have been a typical decreasing trend, but we may be at sort of a minimum point, or it may be going back up for some reason, or maybe there was a little blip and it went up for a little while, but now it's going back down again. We would actually have to have more information to know for sure. Now in example 3, it asks you a different type of question. It says, in what year? Okay, so what does x have to be? Okay, or actually it's asking x plus 1900, right? But in what year is the death rate predicted to drop below 26 per 100,000 in the population? So let's figure if y is 26, because that's your death rate, right? If 26 equals negative 0.560x plus 90.3, what does x have to be to have that equality? And then we know that since the slope is negative, it would go down past that. So that would sort of be the point that we're looking for. So you would plug the 26 in for y and solve for x and get 115, but that's 115 years after 1900. So that would be actually 2015 is when we would estimate that the death rate would drop below 26 per 100,000 in the population. So that is what we mean with least squares and how we can use the least squares line for prediction and for finding a point x when we know the value of y.